We are continuing with this course on optical engineering. So there's a quick recap of what we did in yesterday's class. We looked at basically the importance of studying this subject irrespective of what background or field you may be working in. And we started by looking at the postulates of geometric optics. So we said light travels in a straight line in a homogeneous medium. When will that not happen? If the medium is not homogeneous, and that brought us to the next postulate, which was every dielectric medium has a refractive index associated with it. This in turn brought us to the next postulate. We said in geometric optics what is really important is not just the physical distance that the light is traveling, but the product of the refractive index into the physical distance, a parameter called the optical path length. We came then to the final postulate, which was Fermat's theorem, and Fermat's theorem is basically that light will travel, or Fermat's theorem or Fermat's principle is that light will travel on the shortest path or the path of least time. We then used this principle to arrive at a very well-known law, Snell's law. Now, we also came to a very important observation. When we use Fermat's principle to figure out the way light is traveling, we are minimizing the path, and I can always minimize the path with respect to the optical path length itself, or I could minimize the path with respect to the time. If, however, you are taking it with respect to the optical path length, then you would have the optical path length with respect to some parameter. Let me call that parameter phi for example, psi for example. Okay. Okay. Now I can look at this law that we all know. You have studied Snell's law all the way from high school, right? You should be very, very familiar with it. Fermat's principle still doesn't really explain why Snell's law is true. It stated a theorem, we used that theorem, and using that theorem we arrived at a well-known law. So that might give you the confidence that Snell's law is correct. It still doesn't tell you why it's correct. And really, if you want to understand why Fermat's principle is correct, you have to go back to the wave theory. You can't escape Maxwell's equations. You have to go back to the wave theory. And you are all supposed to have done a basic course in electromagnetics or wave propagation. You might have derived Snell's law in that course. Do you remember what you used there to arrive at Snell's law? You did not use Fermat's principle to arrive at Snell's law, but you would have arrived at Snell's law in some way. Okay, forget Snell's law. In electromagnetics, when you talked about a wave hitting an interface and then you used the Maxwell's equations to figure out what happened to that wave when it hit the interface, what did you use to allow you to calculate that?
Imaginary boundary conditions.
So that's right, you use the boundary conditions. And when you use the boundary conditions in electromagnetics allow you to calculate how much light gets transmitted into the next medium or how much light gets reflected. And there you see already a big difference from geometric optics, because we said this yesterday, geometric optics allowed people to trace the path that rays took. So they could understand concepts of phenomena like reflection and refraction, but it did not tell them how much light got reflected and refracted. Whereas when you go to wave optics, you not only can, you do quantify exactly and accurately not only the directions in which light will take, but also the amount of light that goes in a certain direction. And you can use the boundary conditions to arrive at Snell's law, and there you will understand why. Now, we talked about Snell's law, and generally if you say Snell's law, you are referring to this equation, Ni sin theta I is equal to Nt sin theta t, where Ni is the refractive index of the medium of incidence, theta is the angle of incidence, and nt and theta t are the similar parameters in the second medium. This is actually the law of refraction. Of course, we all know the law of reflection, and again this can be proved both using Fermat's principle as well as wave theory, that theta I is equal to theta r. And a little later on today we will look specifically at how we define these angles, because that's important. Okay. Any questions till now? No? Okay. So, I want to go to the next part, and so we are looking at using reflection or refraction to enable us to design optical systems, right? And before we go down that path, I want to ask you a simple question. It's a simple question, maybe it's not a simple question, but it's a question that we should be asking ourselves, because it's something that we're doing every day. How do we see things? Why do we see things? You're seeing things all the time. You're looking at me now, you're looking at the board, you're writing notes. How do you see things?
When light hits the things, so that can be reflected, so that we can.
Okay, so he's saying that we see things because of reflection, and that's right, right? So if I'm looking at a light source, I could make a distinction, I could make a further distinction. I could say, if the object I'm looking at has its own light, a luminous object, that light travels from the object, reaches my eye, and that's how I see it. But most of the objects around the table is not luminous, it doesn't have a natural light source. How we see it is that light from some source falls on the object, reflects and comes to our eyes. Okay. Now, when we talk about reflection, I can talk about very clean and neat reflection. The reflection that follows that seems, all reflection will follow Snell's law, but from specular reflection, you can easily see that Snell's law is being followed. Specular reflection is a reflection you see from a mirror. You have a nice optically flat, smooth surface. However, most objects are not going to be mirror-like. And what you would get from most objects is diffuse reflection, what's shown in this lower picture here. And yet, whether the imaging system is our eye or a camera, if the goal is to create an image, we must work with this kind of reflection and get a good quality image. So, if I look at, okay, maybe before we go there, let's run through again the angles, the definitions. So, if I had a nice flat surface, so as shown in this green surface here, let's say that's our interface, and light is, say, reflecting off this interface. So, from the incident light, there is a reflected ray, and both the incident and reflected ray are going to lie in the same plane. If this interface is not 100% reflective, then there's also some light that's traveling through, and that is going to continue to lie on the same plane. So, I have a plane of incidence which contains the incident ray, the reflected ray, the transmitted or refracted ray, and the normal that lies in this surface, that is, it's the normal to the interface between the two media. So, if I have a diffuse surface, I can think of having many planes of incidence, because the normal will lie depending upon the particular angle or curvature of the surface. Okay. So, for every ray in a particular plane of incidence, it will reflect in that plane and it will transmit in that plane. And you can see this messy picture that you get down here. Okay. Again, this has just been shown as a two-dimensional picture, but it could be reflecting into different planes. So, this is a reflection of an aluminum foil. It's fairly shiny and reflective, but you can see it's not mirror quality by any means. You can't really make out, there's a person standing and the image has been taken. If it were a mirror, I wouldn't have to tell you here's a person standing, you would see that. Right? So, this is not specular reflection, and yet we see the world around us, every surface that is reflecting light we are not, hopefully you're not seeing images like this, right? That means our eye is able to take diffuse reflection and make sense of it, make proper images out of it, right? So, a very large part of this course is going to look at how do I design optical systems such that I take light that is reflected, maybe as specular reflection, maybe as diffuse reflection, or take light that has been transmitted, and even when it's transmitted, if the surface of the interface is not smooth but has a lot of curvature and variation, when it's transmitted, the plane of incidence may be changing, and therefore the light is being refracted in many different ways. For example, you can imagine you're using an optical system to image just below the skin. Light is traveling through tissue, reflecting off, traveling back through tissue. So, there's a lot of different phenomena that's going on there. There's some reflection, refraction, and there's a lot of scatter. And yet, the doctor has to see a clear image to make a proper diagnosis. So, this course will look a lot, and almost the first 6 weeks will look at how do we design optical systems so that you capture this light in a proper way that gives you a proper image. Just as a recap, in yesterday's class we said what all can we do with light, and we talked about 3 things that you can do with light. You can, yes. Okay, so his question is, how is diffuse reflection different from scattering? So, when I talk about reflection, I am talking about what's happening on the surface of an interface. Okay. Scattering is more a phenomena you talk about when light travels through a medium. The example I gave of tissue, light is traveling through this medium. Now, the scattering happens because the medium through which light is traveling has particles in it, and those particles have certain sizes. Depending on the dimension with respect to the wavelength, you get different types of scattering. But in reflection, we are saying light hits an interface. So, an interface means you had a medium with a certain refractive index, you have now a medium with a different refractive index, or you have a medium where you have, which is the refractive index is a function of position. So, there is an interface, right. So, like I have shown over here, let us say this is Ni incidence, and below this interface I have Nr. Nr may be a function of x, y, z. But at this interface, what happens? The reflection that happens here may be diffuse if this interface is not a smooth, polished interface. Then I talk about diffuse reflectance. If this medium has particles in it of varying size, of different sizes, then as the light travels, it's getting scattered by those particles. So, that's a basic difference. Okay. And it's not that I get information from that light that's scattered. It's not that I've lost that information, but I have to capture that light in some different way or analyze it in a different way. Okay. Okay. So, our goal then is to design optics so that we can collect light in a manner that makes it usable to us. Okay. And I said I was going to write out what are the different applications, main applications, like the very broad applications. Anything with optics in it can be thrown into one of these buckets. So, if I think the first thing you would answer if I asked you what's an application of light, well, it's illumination. Right? The very first application of light is illumination. So, you would have illumination. Yesterday when I asked for applications, some of the first applications people said were camera, microscope, telescope, all imaging, right. So, the whole host of applications that come under imaging, and of course, now there is a lot of use of light in biomedical applications, in medical diagnostics. So, it is again imaging, but you are imaging in order to help with some diagnostic technique. And the third broad area, what would it be? Communication, or let's stick with the I letters, words, information. So the projector here is displaying an image for you. It is giving you information. Fiber optics, which is used for internet, we are using optics to transmit information, and that data travels on the fiber in the form of light, and that carries information. Right? So there are a million examples, but almost any application would fit into one of these three. And imaging here is imaging as well as information. So it's not that you can completely separate these three, but these are the three broad areas. So a very large part of this course is going to focus on the optics required for this, for imaging. Okay. Okay. That the wave model is the one that really explains why things happen the way they do. The ray model doesn't explain why. It allows us to analyze and understand certain phenomena without going into the why, without doing a lot of detailed maths. It works, and that's why we use it, and we use it for a lot of applications. You're going to spend 6 weeks using the ray optics model. When we talk about imaging, what exactly do I mean? So let's say I wanted to take an image of this apple, right? So what does that mean? That means every point on this apple, say I want to image this point. Now if it's not a luminous object, so that means light has to be incident on it from some external source. Let's say I have some external source, light is incident on it. This is incident on the whole apple. Let's just concentrate on this one point. There are a large number of rays that are being sent out from this point. All the rays from this point has to be captured by my optical system and focused to one point. And this is true for every point on this apple. Every point, and you can see how messy this looks. But if I want to create a good image, I must capture all the rays from one point, and my optical system must focus that down to a single point. And that's the challenge. Now it turns out I can never capture all of the rays. It's impossible. I have a huge cone of rays that is being reflected off every point. So my optical system at best will capture some cone of rays, and we'll see the implications or the results of that. All the rays coming from one point on the object must be focused down to one point in the image, and this must happen for every point on the object. Okay. You can see it gets complicated when I have a system where, in this case, I have water here. So not only are all these, here I haven't shown the incident rays at all, right? This fish is not a luminous object, so obviously light is incident on the fish and it's reflecting off the fish. All the rays from this one point here, and now they are going through an interface, so they are bending, so there's a lot more happening. And yet my optical system, whatever it is, must take all these rays and focus it to one point over here. And we must do that for every point on the object. That's what my optical system must do, and that's what you're going to learn how to do in the next few weeks. Okay. So if my object is luminous, it's clear how we see. If it's not luminous, we need an external light source. But how do we see light itself? Okay, just a small aside to get you thinking. How do we see light itself? So, how many of you watch science fiction? Okay, Star Wars. You see images like this. What's wrong with this picture? Star Wars is famous for its lightsaber. There's something very wrong with the lightsaber too, but we'll not go into the lightsaber. What's wrong with this picture? This is a starship out in space, and here's this laser beam. We try to use laser beams for non-violent things, but here's a laser beam, presumably as a weapon being shone somewhere. What's wrong with this picture? You're saying something. So how do we see light? Actually, we see light through scattering. Right? It scatters off particles in the atmosphere. So say in this room, right now it's fairly well lit, but say the room was dark and it's brightly lit outside and there's a gap in the curtain and some sunlight comes through. You often actually see the ray of sunlight. Or we live in a beautiful campus, you go out for a slightly early morning walk, you'll see the sunlight filtering through the trees. Now you could see it in different ways. You could see the patch of light on the ground. That way, how are you seeing that? There's reflection and the reflected light is reaching your eyes. But you often actually see the passage of light. Now, when you go for a walk in the campus, or if light was filtering through this room and you saw the passage of light, you would see it because it's scattering off maybe dust or particles in the air because of scattering. Scattering is an important phenomenon. It's not always bad. I wouldn't see things if there was no scattering sometimes. But in this picture, this is out in space. There's no atmosphere here. So while the light is leaving this place, and maybe there's some scattering or reflection just as it leaves. So at the edge, you may see some reflected light, and the light may reach your eye because of that. So you may know that there's light leaving this point. But you shouldn't actually see this path of light because there's nothing for it to scatter off. Okay? So, as I said, we are going to concentrate on geometric optics for imaging. Okay? So, any optical system, we start off by saying every optical system has what we call an optical axis. Okay, this is a straight line that runs through the system, and I'll be more clear and say runs through the center of the system. Okay. Sorry, what is the optical axis? That is the line through the system that if you sent a ray, the ray would travel undeviated through the system. Okay. So if you consider a lens, and if I had a ray that was traveling like this, you know the lens is going to bend the ray. Right? If I have a mirror and I had a ray traveling like this, you know that it's going to travel in some angle. The optical axis is that line which travels through the center of the system. I haven't really drawn it through the center, but I hope you understand what I mean. Right? It is the path that a ray would travel undeviated through the system. I can use a mirror to change the direction of the optical axis. Okay. In most optical systems, or I should say in many optical systems, the optical axis is also the axis of symmetry. Okay. This is because a lot of our optical elements are circular in nature. So this does not have to be true. I can have non-circular lenses. I can have cylindrical lenses, for example. I can have optics that is not circular in nature, but a lot of our optics is circular in nature. We take microscopes, cameras, the lenses will be circular in nature, and therefore more often than not the optical axis is also going to be the axis of symmetry. Okay. You can even think of it as the axis of rotation, if you will. Okay. Any optical system has a pair of conjugate points. So, if I think of the optical axis This is my optical system. I'm drawing a lens. That lens is representative of an optical system. It does not have to be a single lens, could be a number of lenses. So, if it is an imaging system, that means if I have a point source S and it is getting it imaged at a point P, that the conjugate points are S and P. This means that if I were to put the source here, the image would form here. So, the optical path is reversible. So, this is the reversibility principle. Now, while the path is reversible, that means source is at S, image is at P, or source is at P, image is at S, the quality of that image need not be exactly the same. The locations will be the same, but you could design the optics such that it gives you a better image when light travels in one direction as compared to another direction. Okay? So, this only tells us where the locations will be, and that won't change, and that is a pair of conjugate points, but don't think that means that the optical system works exactly the same way irrespective of the direction. Okay. Now, what is the goal of any optical imaging system? You want to collect light and create an image, and you want to create as best quality an image as possible. That's your goal. Ideally, I want to collect all light. Okay, so this is the ideal goal. This is ideally what I want to do. But I can never ever collect all light. If you take this example over here, let's say I have an object over here. I have light traveling, so there's light incident and then there's reflected light, and it's reflecting in a very large cone. Some fraction of that gets through this optical system. Okay, and you learn a few classes on that. You might think, okay, I have drawn this set of rays, this cone of rays, where the upper ray hits the top of the lens and the lower ray hits the bottom, and this cone is the cone that will now travel all the way through the system. But it could be there's some element later on in the system that blocks this part and this part. So, it actually could be some much smaller cone that is making it through the system. Okay. So, we will look at that later on, but the point to take is never do you collect all of the light reflected off the object, you only collect a part of the light, and the most that you can collect with a particular with a particular optical system, we call that a diffracted limited image. So, that is the best you can do. The amount that you collect is limited, and we won't go into the details of that process in this course, but it's limited by a phenomenon called diffraction, and that's why the best image you can get, if there's nothing else wrong with your optical system, if your lenses are perfect, your mirrors are perfect, everything is in exact place where it should be, then you have a diffraction limited system. So, that's the best you can do. This also relates to the resolution with which you can image. Clearly, I want my imaging system to have a high resolution. I want to capture the fine details in the object that I am imaging. Optical systems are limited by the wavelength of the light that you are using. So, rule of thumb, you can say roughly lambda by 2, where lambda is the wavelength. Lambda by 2 is the best resolution that you can get with an optical system. But optical systems are not the only way you can image, right? Do you know of any other ways of imaging, non-optical? You can use electron microscopy, right? Again, the resolution is determined by the wavelength, but it's a wavelength associated with the electron, and that's orders of magnitude better, right? So in optical microscopy, your best resolution with a very good optical microscope would be in hundreds of nanometers. With an electron microscope, you can go down to tens of nanometers. Okay? You can use ion beam microscopy, again tens of nanometers. You can use atomic force microscopy, again very high resolution. Right? So you have many different ways of imaging, but in optics, it's diffraction limited, and you are stuck with around lambda by 2. Even here I have to say that in the last 10 years or so, people have taken optical images and then used computational methods to get what is called super resolution. Okay. So then you can you will capture optical images with the best resolution you can, and then you can improve the resolution using some computational techniques. So this is a big area of research right now. Okay. Funnily enough, in 2014, a Nobel Prize was awarded to somebody called Stefan Hell from Germany for a technique called STED microscopy. It was actually awarded, I think, in chemistry, the Nobel Prize, right? And he used diffraction. So we say optical systems are limited by diffraction, and therefore you can't get better images, but he actually used diffraction and improved resolution. Okay, so it's a very clever, and once the technique is explained, a very simple technique, and you think, well, anyone could have thought of this, but of course Stefan Hell did. So maybe if we have time later on in this course, we'll look at this technique in some detail, but in this case, diffraction is actually used to develop some element that could be used to improve resolution. So the main point is, in an optical system, wavelength is what will limit your resolution. There are other ways of getting much better resolution, but in an optical system, this is what your limit will be. Okay. One way to think of this is, if I had, since the resolution is limited to lambda by 2, you can think of, let's go to lower and lower wavelengths, right? And people do that. Some of the more sophisticated tools use ultraviolet, UV, so you're going to lower and lower wavelengths. But of course, you can't always use lower wavelengths, right? How do you think of geometric optics then? We think of geometric optics as, and even when I say lower wavelength, you're saying you're reducing the wavelength, but reducing it with respect to what? Right? So it is reducing the wavelength you're using for imaging with respect to the size of the object that is being imaged. So the size of the object in relation to the wavelength, that is what will determine your resolution. Okay. So in geometric optics, we say, because in geometric optics you're talking imaging of large with respect to wavelength, you can consider lambda is equal to 0 here. Okay. That's an assumption we're making, because the wavelength is so small compared to the objects that we are typically imaging. Okay. So that's an assumption that we're making. So if I'm imaging objects in the order of nanometers, I cannot make this approximation, and geometric optics will not work there. I have to go to wave optics to explain what I'm seeing. Right? I mean, you would have seen, if you take a CD or a DVD, right? If you hold it against the light, you see it splits up into colors, right? Their structures on that are in the order of hundreds of nanometers. Right? It's not a geometric optic phenomenon that is splitting up that light. So I can't use geometric optics to explain. So only where that condition is satisfied can I use geometric optics, and that's what we are going to do in the first part of this course. Okay. Okay. So if I'm talking about an imaging system, we have already said that clearly any imaging system has to capture as much light as it can from any point, from every point on the object, and all the light from that point of the object has to form one point in the image plane. Right? If one point in the object plane forms 10 points in the image plane, I have a blurred image. Right? So, of course, what is very, very important in any imaging system is the focus. Okay. So, what element can I use that will provide the best focus? Right. So, let us take, first thing I will do is always draw my optical axis, then I am going to take just one interface, okay, and I say I have a point source here, light travels from this point source to this interface. So, it is an interface, that means I have refractive index N1 here, and right now I am not limiting it, right. So, it is just an interface. So, after this interface it is completely another refractive index N2. We are talking about homogeneous media. So, it is N1 on one side and N2 on the other side. Okay. This travels to some point over here. So, this point I will call S, this is P, and this distance to the vertex of this interface, let us call it S naught. Again, from vertex to here we will call it S, let us call it Si. This is L naught, this distance let us call this O, and this is Li. Okay. The optical path length of the ray travelling along the optical axis, right, will be N1. So, this is optical path length, N1 the refractive index into the physical distance S naught plus N2 into the physical distance in this medium, which is Si. Now, our goal is every ray coming from this point S should arrive at point P. In other words, for the second ray that I have drawn, this should be equal, the path length should be equal. So, N1 into L naught plus N2 into Li, and this should be true for any ray that I draw. If I drew another ray like this, from S and all the way to P. You agree with this? If every ray travelling from S reaches P and this condition is satisfied, I am saying the optical path lengths are equal. Then I would say this interface that I have chosen, it is not a flat interface, it is an interface with some kind of curvature. This interface that I have chosen is doing the job of imaging. Now, does such an interface exist? It turns out it does, right? And the interface that satisfies this condition is called a Cartesian oval. You can think of how it works if you break it down, look at this. if you have rays traveling along the optical axis and a ray traveling at some distance, this ray hits the interface before this ray does, right? So, the ray along the axis enters the interface and starts traveling slower, while this is traveling slower here, this ray is still traveling faster in air. By the time it reaches this interface, this ray has already traveled some distance within the interface, right? Oh, sorry. What is exactly happening? You can see that the wave that is hitting this interface is going to bend because this has traveled to this point, this is still traveling at a higher velocity, this is slowing down over here, and so there is a bending of the wave, and that is what that interface is doing. That is what any optics does, right? It changes the shape of the beam that is incident on it. It changes a wave that is diverging into a converging. It is creating that focus. Okay? So, that is the primary goal of what we are trying to do. Okay? So, I think we have run out of time. So, we will continue in the afternoon class at 2 o'clock. Keep this image in mind, we will continue from here, right. But the goal is to shape the incident beam, either to collect it and focus it to a point, or shape it to give us some particular application.